So hello, I am Arsit and today I will be briefly discussing principal component analysis or PCA. It is a feature extraction technique. Okay, so what is a feature extraction? So if we have n number of features and we are considering only m number of features in which m is smaller than n, so it is a feature extraction technique. Like if we have many features, we are extracting some of the important features from those for less hardware complexity or for better performance of our model. So PCA is also a machine learning unsupervised machine learning model. Unlike other machine learning models, like which is used for prediction or classification of something, some data sets, PCA is used for reduction of attributes, or you can say reduction of columns or features, anything. So let's take some examples first, so that we can understand what is the actual motive of our this machine learning algorithm. So first, let's consider a data set name as placement, and if we have a IQ column, CGPA column, or let's take a column headphone, okay, or let's take a column locality. Another column is number of chairs or anything, and the last column is a label or target column placement. So this column will be showing if the person is placed or not placed, 0 1 or yes no, something like that. So if you guys carefully think, then IQ is an important question, important column, which let's consider if a company came to some college for selecting some of the students for their company. So IQ is an important attribute that company will consider for selecting that student. So IQ is an important column. If IQ is high, then there is a more chance of that student to be selected. CGPA. CGPA is also most important attribute nowadays. Headphone. Headphone is directly not uh, contributing for the company or for the student to be selected or not selected. Locality. It is like a 40 or 60% chance that if the company came for selection is from same locality where from where the student belongs to. This may matter or may not matter to some company, depends upon the company, or if there is a work from home option. So this is, let's take matters or don't matter. Okay, number of chair obviously doesn't matter. Okay, this is a placement section, if the student will be placed or not placed. So as you can see that this column is important, this column is important, this is not important, this is not important, this is not important. So if we will considering headphone column or number of chairs column for training our model, it will actually decrease the accuracy of our actual machine learning model or deep learning model, and it will also increase the hardware complexity. So in in PCA, we actually neglects or reduce the unnecessary columns from a data set, or if there are so many features, we will neglect or remove those features which are not most necessary for training of that data set. Okay, this is first example. Let's take another example, option 2. If a company is going to IIT Bombay, and there are all the columns are same. Let's only take an important column, IQ, CGPA. Uh, the company is actually making a chart after interviewing, and they are including a column name as name of college. And let's consider that company will be giving this data set to some machine learning model, uh, so that the machine learning model will select the student. for that company. And here is selection done or not selection. So do you think this column, name of college, will actually contribute to the result in selection column? Do you think? Actually, if there are 20 students, let's take 20, 1, 2, 3, 4, 20, some CGPA, but name of college for every student will be just IIT Bombay, IIT B. So if you carefully notice that the variance in this case is 0. There is uh, no any difference in uh, in the this column. There is no separate values in this column, so variance is 0. So and also this column is not contributing to our result section, because if all the students are only from IIT Bombay, then why do we need that column? So from here we can conclude that variance is a necessary condition for a attribute or feature to be in that data set. Data set. Okay. Okay. So you guys hopefully have understood why do we need a feature reduction technique. There is a term known as a curse of dimensionality. So according to curse of dimensionality, as the number of dimensions increases, data becomes sparse, making it harder to learn patterns. So if we have so many features, then machine learning model will not understand that which features are important for the for prediction or classification and which one is not important. So this is curse of dimensionality. The second importance of PCA is data visualization. So if we have so many features, we can't visualize the data. Like if we have 2D, then we can obviously visualize the data. This is one cluster, this is another cluster. If we have 3D, this is one cluster and one cluster is behind this and third one is this. So up to 3D it is possible to visualize, but after 3D we can't visualize the data. If we have 4D or 8D, there are 19 20 features, we can't visualize the data. And you guys should be knowing importance of data visualization before applying any machine learning algorithm. So this is the second most important thing. That's the reason why we need a PCA technique. So third one is computational complexity. Obviously if we have more number of data points, more number of features, there will be high complexity for computation. Multicollinearity, if two data points are highly correlated, it will also affect the model. We will discuss this in later portion. So the main motive of PCA is to preserve the as much as variance as possible. If a feature have so much of variance, it will contribute most in the result part. As we have seen in this example, if there was same college, it wasn't contributing to the result part because everybody belongs to same college. So it doesn't matter to company that college thing part. Okay, so okay, now first let's first discuss sorry let's first discuss the important key concept we should be knowing before studying this PCA. The first one is variance, we have already studied. Second one is covariance, we will be studied. Third one is eigenvalue. Fourth one is eigenvector. Okay, variance is how much data point is spreaded from its mean. Like if let's take an example, if this is a mean, this is mean, and our data points is like this. In this case our data points are like this. So as you can see that in example 1 it is covering more area, and distance from the mean is so different for all the different data points. Like this one is 10, 5, 2, 3, but in this case almost all the data points are just gathered near its mean. So this one has high variance, this one has low variance, high variance, low variance. Okay, what is covariance? Covariance is just like variance. uh, in variance we take the relation of data points from the mean value, but in covariance we take check if two data points are correlated to each other. If x1 x2 are two data points, how is x1 related to x2 and vice versa? We will see eigenvalue and eigenvector in later part. Let's continue the algorithm first. So okay, so there is an important term, principal component. Let's first let me give you a visual intuition. What does this algorithm do? So if let's take a graph, let's plot data points. Okay, so this is one of the attributes I have plotted. So I have made a projection of these data points on both the axes. This one is y-axis, this one is x-axis. So as you can see that variance of these data points on y-axis is very less as compared to on x-axis, right? So if our initial principal component was this one, y-axis, it's like we have considered a eye view from y-axis, we will change it to x-axis so that the variance will be maximum, and it will be easy for for a machine learning algorithm to consider attribute to be important or not important, or for us to drop a column or attribute. So we will be discussing this part later on in more detail. So let's first study all the steps we take for a feature reduction. First one is standardize the data. So why this generally people don't consider this step to be important, but I think this is the most important step. Like let's consider another example. Uh, if we have fuel, distance, speed, this is any data point, and this 3 is the attribute in the data in that data point. So fuel will be ranging between 0 liter to, let's take, 20 liter. Distance will be uh, 0 kilometer to 1000 kilometer. Speed will be from 0 kilometer per hour to, let's take, 100 kilometer per hour. Do you think if we will upload this data set in any machine learning algorithm, then the machine learning algorithm will be working fine? Obviously not, because the fuel section will be lower values, the distance will be from higher values. Let's take uh, last second data set. This one is n minus 1 data set, and the fuel left is 5 liter. Distance is 990 kilometer. Speed can be anything. Let's take 80 kilometer per hour. So distance is a larger number, so this will affect more in the machine learning algorithm. The machine learning algorithm will think that this is the more important thing because it's changing too much. if distance is changing from 0 to 1000, so it's a large distance, so machine learning will think that this is an important attribute, but maybe it is not an important attribute. So we need to standardize the data. So in this, so I hope you guys got why do we need this step. So if feature on different scales, those with larger ranges will dominate the principal components, leading the misleading results. So we, so what is the formula of uh, standardized standardization? Sorry. So a scaled data x scaled is equal to x minus mu by sigma. So here x is our data points, mu is our mean value, sigma is variance. You already know mean, you already know variance. Data point will be data point, and new data points will be x scaled. So I have actually solved this one, so you can see here. So x is the original feature value, mu is mean, sigma is standard deviation. So after this, mean will become 0 and deviation will become 1. So here is the example. If we have data points 150, 160, 170, 180, 190, we will first compute the mean value. Mean will be sum of all the data points by total number of data points. So total number of data points is 5, and this is sum of all the data points. We got 170 as our mean. Then we will compute the variance or standard deviation. Variance is sigma square and standard deviation is sigma. So here we are computing standard deviation. So we know the formula of variance. Formula of variance is sigma square is equal to summation of x minus x bar whole square by n. So so you can see that x is a data point, x bar is mean. So here is 150, the first data point, minus mean whole square, second data point minus mean whole square, and similarly for fifth data point minus mean whole square divided by 5, and our variance is 14.14. The third step is standardize its value. So we have computed all the thing. X scaled was equal to x minus mu by sigma. So we will put values here for every data point, and this is our new scale data point, which ranges from which ranges from only minus 1.41 to 1.41. So now the transport value mean 0 and standard deviation 1. So this is a coding part we will discuss later on when we will be uh, on the laptop. So we are done with the first step, that is standardization of data points. So I hope you guys are understanding what we are doing till now, and why, what is important of PCA, why do we need to standardize the data. So the second part is compute the covariance matrix. Okay, so what is covariance? I have already taught you in the previous section. So what is the covariance matrix? First of all, let's understand the formula of covariance. So covariance between two data points, that is x and y, is given as 1 by n, where n is the total number of data points, summation of 1 to n, and xi is the data point, x bar is the mean of, sorry, x is attribute, y is attribute. So x bar is feature, x bar is the mean of that feature, y bar a mean of that feature, another feature, and these are the individual data points. So overall the formula is 1 by summation of 1 to n. X means that data point minus mean of x, similarly y minus mean of y. We will be taking an example later on. So this is the formula of covariance. So let's study why is this covariance matrix important. because it captures how different features vary with respect to each other. Okay, the covariance between two feature x and y is a measure of how they change together. So same thing. I hope you guys has got. So this is an important line. A positive covariance means that one feature increases, the another feature also increases. If we have got covariance as negative, then if one feature increases, the another feature will decrease, or vice versa. So let's take an example first. Okay, so if we have two features only, then we use this formula. If we have more than two features, then we use this formula. And this is also easy for computation purpose, like for computer, this part, the calculation of covariance with this formula is actually easy. So in this, x is a standardized data matrix. This is important thing, that this should be a standardized, not the actual x value. Xt is transpose of x, and n is total number of samples. So one of the most important question we are asked after reading the PCA is, what is the dimension of covariance matrix, and that is D into D, or F into F, feature into feature. So let's first understand what is a covariance matrix. Okay, so covariance matrix, let's denote it with sigma. First of all, we have covariance of xx, then covariance of xy, then covariance of yx, then covariance of yy. Actually, covariance of xx, covariance of yy can be written as, sorry, variance of x, variance of y. So all the diagonal values will be variance, and this will be covariance. The another thing is that this one is variance, and this one, sorry, this one and this one will be covariance, and this will be actually a symmetrical matrix. Okay, so I have written this for only two features. This one is for a larger feature. This is the same thing. The diagonal will be variance only up to last, and this will be just like a normal matrix. Covariance of x2 x1, covariance of x3 x1, x3 x2 x. If we will be writing covariance here, then it will be covariance of x3 x3. Similarly, covariance of x3 x4, like this up to xn. So this is a covariance matrix, and its dimension will be number of features into number of features. Remember this. So this is a small calculation part. Consider a simple data set. This is a data set having two features, x here, y here. So first tell me what will be the size of covariance matrix. We have two features, so covariance matrix will be 2 into 2 only. We will see later. So there is two features, that is two columns, four samples, that is four rows. Like this one is sample. Okay, we have done from the starting. We are standardizing the data, mu1 mu2 x entered value. This one is x entered value for feature 1, feature 2. Compute the covariance matrix. We are computing with this formula, and after getting this matrix, we can easily compute through this formula. What is x t center means x transpose center into x centered, that is minus 2.25 into minus 2.25. Actually this is a minus 2.25 its xt will be same as this one, that's why we are getting like this. You guys can compute by yourself and the answer will be same. So this is by 4, that is total number of samples that we have. And this is a covariance part, this is covariance part, this is a variance, this is variance, and overall we get covariance matrix like this. So what does covariance matrix tell us? The variance of feature 1 is 2.8, the variance of feature 2 is 4.8 to 1 to 5, the covariance between two features is 3.1875, indicating a positive relationship. Means if one feature will be increasing, then another feature will be also increasing. So this is the coding part. So step 3, compute the eigenvalue and eigenvectors. uh, so what is the eigenvalue and eigenvectors? Let's understand this by an example. If we are linearly transforming any vector, like we know that our normal number line is like this only. If we have changed this to this, like this, okay, and this is the x-axis, here this is the x-axis. If initially this is our origin, let's consider this as our origin. If we were having this as a vector, so where the vector in transformed plane will appear, like it will not appear here obviously, no, it will go here. Or if we change the plane, it will go anywhere, like it also can go to opposite direction, depends upon the transformation. So the vector, there will be some vectors which will not change its direction, even change in the transformation. So that will be our eigenvector, and the value of that eigenvector will be the eigenvalues. I think this explanation is a little complex. Let's just study with the document. Why is this step crucial? Because determine the principal components of direction of maximum variance in the data. So okay, let me explain this by a simple example. If we have this data point, so like if we make a principal component like this was our variance, now this is our variance. So this is the maximum variance. We have created a PC1 and we will forget this one. So this is our new principal component through which we will be analyzing data further on. So eigenvalue indicate the amount of variance explained by each principal component. Eigenvector represent the direction axis of new feature space. So in new feature space, what will be our new axis? This will be the eigen vector's direction. This will be new eigenvector, and the value of this PC1 will be showing the variance part, how much variance we have in this direction. So I hope you guys have understood now what is the importance of eigenvalues and eigenvectors. I hope you guys already know how to compute eigenvalues and eigenvector. We have studied this in class 8 only. So this is just a computation part. You guys can pause the video and check it. If you will not understand, I will explain this in another video. So we have this was our covariance matrix. So we have minus pi lambda I is identity matrix. So this becomes the a11 minus lambda 1. This become a21 minus lambda, and we have computed the value of lambda. So lambda 1 is 7, lambda 2 is uh, something 0.625. So this is our eigenvalues. First eigenvalue, second eigenvalue. Now we will compute eigenvector. The formula for computing eigenvector is this. So after computing eigenvector, the first for lambda 2, that is 0.625, our eigenvector becomes this one. For uh, for first eigenvector, actually I have not computed. Oh, here is the second eigenvector. So these two are the eigenvectors corresponding to its eigenvalue. So what is the interpretation of eigenvalues and eigenvectors? So eigenvalues 7 point, sorry, it's 70 point something. Where is it? Okay, it's 7 point something. So I have already told you that eigenvalues, ignore this one, this may be wrong, tell us how much variance is captured by each component. Like if we have principal component like this, PC1, PC2, PC3, and we have data points like this, so obviously PC1 has more variance than PC2. And like let's take, this is our PC3. PC3, this has so much less variance, like so PC3 has less than PC2 and PC1. So we will be considering only those principal components which has maximum variance, and the rule said that we should go up to 90% of variance. Like if PC1 have 20% variance, PC2 has 15%. Similarly, if up to PC8 we got total sum as 90% or above, then we can consider or decrease the number of features to 8. If we have 20, it will decrease to 8 only. So you have seen that how do we reduce the number of features or attributes. This is choosing the number of principal components. This is the same thing I have told you, just for every start from the top PCA, top PC, and start adding it, PC1, PC2, up to where it got 90% or above. So here they are telling 95% or 99%, depends upon the model. So here is a overall total example calculation, and as you can see that the first component was 4.5 PC1, and it is covering 50% of variance. If we have taken two components, it's covering 75.5. If we have taken three components, it's covering 88.8. If we are taking four components, it's taking almost 96.6. So the feature is reduced to four components. So this is the last four. So now why do we need PCA? What are the applications of PCA? We have already discussed this thing in the first part. Let's discuss it again. First one is data visualization. Obviously it helps to visualize the data in 2D or 3D for easy visualization. Noise reduction, by removing components with low variance, PCA eliminates noise from the dataset. We have already studied this one. Third one is feature engineering. PCA generates new features, principal component them that may involve model performance. Improve model performance. We have studied this too. Speeding of machine learning algorithms. So reducing dimensionality reduces the computation time and storage requirements. We have also discussed this one in the initial parts, computation time and storage requirements. So this is just use case, don't read this one. So next we have kernel PCA and kernel trick. So I will be teaching these topics in some other video. At last, thank you for this opportunity. I hope that you all or whoever is watching this video has got the clear idea how PCA works. And this is a demo video, that's why I am using this document or notes form. But actually, I will be using slides or PPT. So, thank you. Have a great day. Bye.